Okay, hi everyone. Uh, Only one person is here. I appreciate it. Thank you for coming. And I'm sad that people haven't shown up. Uh, I don't know whether it's because of the weather or because people are studying for grades only. I don't know if it is because of grades. I'm sad about it because I'm trying to teach with passion, and I always have said that grading is not important in this course, right? Because I'm a good grader, and it's just the purpose of this course is only learning with joy. And but if it is for the weather, then what would you do in winter? This is just fall in Canada. Okay, but anyways, let's start. So last session we talked about reinforcement learning. Now we continue, but at the end of the last session we had Q learning, but let's review that again from the start of Q learning. I think before that we also had Q function. Let's start from the Q function. Okay, so we said that, do you remember I said for understanding, hi, you're the second person in the course now that I've joined. No one else. Yeah, maybe. Thank you for coming. I appreciate it. So I said in reinforcement learning, what did you say? We for understanding the topic, you need to understand the essences of the things. That it's also called dimension of the things. For example, in physics. For example, in physics, it's very important. You can even you can derive the formulas using this technique. What do I mean? So for example, if the left-hand side is kilogram per second, then the right-hand side needs to be kilogram per second. I saw a YouTube video which derived one of the hardest formulas in physics. It was about, I think, black holes using just this technique, the matching dimensions. So it's a good technique in physics, especially. Now, as I said here, in reinforcement learning, we have at least two important essences. One of them is action. One of them is reward. So for reward, I introduced three things. Do you remember reward itself and value and state action or Q. So reward, value, and Q. They are in the essence of reward. And for action itself and policy. Exactly. Thank you. So here, then I said, whatever we have for value in reinforcement learning, we can have it for Q function, right? For Q function. So this is Bellman's equation for value. Do you remember? Then I said, let's replace value V with a Q function, a state action value Q function. So here it is. Rather than V, I have Q, S, and A. Note that V value is a function of a state. Why? Because it's the best reward that I can get in this state, right? So at every state, you have some best action having the largest reward. And that is the largest reward at that state is value. But Q function is a function of state and action, both. So it's not the best reward necessarily. For different actions, you have different Q values. And now, rather than V, I put Q. But here, in the right-hand side, rather than V S prime, I put maximum of Q S prime and A prime with respect to A prime. Why? Can you tell me why this maximum came? Comparing these two. It's because value is the best reward, the largest reward. Q, S, and A is not necessarily the largest reward. But when you say maximum of Q, S prime, A prime with respect to A prime, it means that the best action which maximizes the reward, right? So, and maximum of Q is in the essence of reward, which is also this. V is also in the essence of reward. So this justifies why we have maximum here. And so, as I said, also we can have Bellman equation in terms of, so if we can put the best value V star in the Bellman equation, likewise we can have the best Q in the Bellman equation, right? Then I also said So maximum of Q star SA with respect to A, the maximum is in the essence of, the maximum of Q is in the essence of reward, right? The essence of Q or in the essence of reward. As a result, it is V star. But what about argmax of Q star S and A with respect to A? Argmax, argument. Argument is action, right? So it's in the essence of action. That's why in the left-hand side, I have policy. Right. And also I can say that this is the total discounted rewards, right? So which argmax of this with respect to the policy. So it also gives you the policy star. When we say star in reinforcement learning, it means the optimal, right? Optimal policy. And then we said, do you remember incremental update that we had? We already talked about it in the previous session. For the value V, we can have it for Q function as well. As I said, whatever we have for value, we can have it for Q as well. And what was GN? It was the total discounted reward in the horizon. And then we said policy iteration using, do you remember we had policy iteration using value V? We can have policy iteration using Q function as well, right? And what did we do for policy iteration? Do you remember? Forget mathematics, forget this. Whatever you want to improve in life, what do you do? How do you improve things? What? You exactly. You evaluate it, see how good it is, then you improve it. But by improving that, it changes. So you need to evaluate it again. Then you see how much it, hopefully it has improved, then you improve it further. But by this improvement, it changes again. You need to evaluate it again. So it's an iterative approach, evaluation, improvement, right? So that's why. Now this is my policy that I want to improve. But how do I evaluate the policy? What determines whether a policy is good or not? Value, reward, Q, whatever, right? So if reward is large, if value is large, or if Q is large, the policy is good, right? So by in the policy iteration using value V, we used V, Bellman equation for value V. But here, for policy iteration using Q function, we use Q, Bellman equation of Q function. And policy improvement says that, so by the way, for policy evaluation, I'm using the incremental update here of Q function, right? And for policy improvement, I say argmax of Q with respect to A. So it's in the essence of action. So it gives me the policy, right? And it converges, right? After a while, the Q doesn't change much. The policy doesn't change much. Then Q learning, we said, do you remember what? Which slide?
Yeah. You're searching, I guess, like a lot of random values for both S and A.
So initially, as you see, I have initialized the Q with a random value for every state and action. For every state, you have a bunch of actions, right?
Yeah.
And let the Q be random. What do I mean? The rewards of different actions in different states, let them be random. Because initially you don't know what is the best action to do, right? If your Q values are very good by chance, it converges very soon.
Mm-hmm.
And this amount of delta becomes a small. Agree? Again, forget mathematics.
Sorry, that what you just highlighted there, that's like the discounted reward in the future.
Which one? No, this is the discounted rewards.
Yeah.
So basically this amount, if Q is good, this delta becomes very small. If Q is awful, this delta becomes large. Again, forget mathematics. You wanna change Ben. What do you do for Ben? The previous Ben plus some delta, you put it in the next Ben until convergence. Okay, until convergence of Ben. What does it mean? Initially assume Ben is awful. What happens? And delta is changing in every loop, right? So again, forget mathematics in real life. You have some Ben and you wanna change it. in the unit change, and delta changes in every loop. So initially, if Ben is awful, delta is large, but gradually Ben improves and improves until delta becomes smaller and smaller, where the previous Ben and the new Ben will be almost close to each other, right? This is exactly the iterative approach that we're having here.
So they're kind of saying the current iteration is very close to, I guess, future discounted reward.
Are you talking about this part?
Yeah, and then like find some alpha.
So it says that the GN is in the essence of reward. So the total discounted reward that you have and the reward that you can get by the policy pi at the state S and doing the action A. Okay. If this is a good estimate of the total discounted reward, then this difference becomes almost zero. Right? But if it is an awful estimate, then this delta is large.
And then, sorry, what was the alpha n there?
Alpha n is a learning rate. They call it learning rate. Oh no, it's not gradient descent. But you can see it as alpha n can scale the delta. We call it learning rate.
1 over.
So it can be 1 over n, and where n is the number of times that the state S and action A are observed together. But it can be any function satisfying those two sufficient conditions. Do you remember? Do you remember? No? This one. Do you remember? I gave you some example. So 1 over n satisfies these two conditions. Basically, it says that the larger n, the smaller the learning rate becomes. Right? But satisfying these two. Did I answer all of the questions? Okay, so then I said, consider these. What was it? Do you remember this? What was this? This is Bellman equation, and I said we can approximate it by one sample in Monte Carlo approximation. So this expectation can be approximated with R, right? And this one, for one sample, I only have one next state, S prime. So for one of them, it becomes 1, the other probabilities become 0, and the summation goes away. So it becomes V S prime, only one of them, right? With the gamma behind it. Do you remember? We talked about it in the previous session. So likewise, we can have it in the Bellman equation for Q in equation 26, where we are using only one sample, right? And do you remember we did this for finding temporal difference out of incremental update for value V? We can do it the same for Q. So basically what I did for value V, I'm doing it for Q. So it gives me equation 27. And what is that? This is a temporal difference evaluation of Q, right? And by the way, let's compare it with the update of value in value iteration. Do you remember the value that we had in the value iteration? It was this. Let's compare these two. What do you see? First off, let me tell you this. You remember we said value iteration and policy iteration, they are used for, was it for Markov decision process or reinforcement learning? What was the difference of Markov decision process and reinforcement learning?
The transition model.
Transition model, right? So we can have the transition model. What is the transition model? Going from one state to another state. What is the probability? Okay. So now what? So I said in Markov decision process we have the transition model. So we are using this. So we have two main algorithms for Markov decision process. One of them was value iteration. One of them was policy iteration. For reinforcement learning, we have two main algorithms. One of them is Q learning. The other one, we'll see that. We'll see that. That is called policy gradient. We'll see that in a few slides, okay? So now let's compare the value iteration in Markov decision process and the Q learning temporal difference of Q learning in equation 27 in reinforcement learning. Equation 27 and this one. Do you see the difference? We are using Q here, but previously we used V. what is the intuitive justification here? The interesting fact is that in Markov decision process, it's easier, and it's an easier problem because we have more information, right? So value suffices for us, which is depending on S, right? But in reinforcement learning, we are confused. We don't know what is the best thing to do. We don't have a transition model. It's a harder task. It's a more realistic task. As a result, we use Q function. Do you see the beauty? So here is the justification. And Q learning is nothing but that update of Ben, right? Ben is the previous Ben plus some alpha delta is the next Ben. Now replace Ben with Q. This is exactly Q learning. So this is exactly how we update things in real life. And so while Q star is not converged, select and execute action A. And this needs some discussion, I will tell you. Assume we somehow find the action A, and then by doing this action, we see the state of the environment changes, right? To S prime. So we see S prime, the next state, and the reward, the current reward, right? NSA increments. Why? Because one more time we saw state S and action A together, right? And alpha becomes 1 over NSA, right? And this is a temporal difference that equation for Q, right? And then S prime with set S to S prime, meaning that we go to the next state, right? And we do it until Q star converges, until it becomes converged. And now let's talk about this one, action A. So as I said, there are two approaches. Either we select action A randomly, right? What happens? If I select action A randomly, it means that I explore the whole options that I have, right? Then it is good for exploration. So when you do that, you will converge later. You will converge later, but at least you explore. So you are slower to converge, but you explore. But what if you select action A as the best action? What do I mean by best action? Can you tell me? I have written it here because you have Q here, right? So at every iteration, I have some Q star. I use that, although it might not be the best, but I use that, right? And argmax of Q star SA with respect to A. So it's in the essence of action. So it gives me the action, and this is the best action based on the current Q. But what happens? It might get stuck in the local best, right? So it doesn't explore different actions. So it's good for exploitation. It converges fast, but we might get stuck. So we always have the trade-off between exploration and exploitation in optimization. And as a result, let's have the best of two worlds by saying that. So first off, you tell me, initially, is it better to do exploration or exploitation initially? Exploration, exactly. Because we are far away from the solution. We want to search different options that we have, but later we need to do exploitation. Why?
It's very near to the best solution.
Yeah, exactly. Thank you very much. So we are close. We are supposed to be close to the best solution. As a result, we don't want to oscillate around it. So initial exploration, later more exploitation. Now, as a result, we can have a combination of both, saying that with probability epsilon, let me do a random action. With probability 1 minus epsilon, let me do the best action by this. Okay. So, and we also can change epsilon. Initially, epsilon should be, so this is exploration, right? And this is exploitation. So initially, epsilon should be large. But gradually, we should decrease epsilon, right? This is called epsilon greedy algorithm. Why is it called epsilon greedy, not 1 minus epsilon greedy? Because when we do random action, we are greedy to search this whole space. Right. And this was an example that we talked about. I don't go into much details, but this was a game. This game is also called random walk. And we said that we showed with this game that how interestingly it changes the QD right. What was the game? Let me tell you briefly. So we start from the state D. The terminal nodes are A and G. A loses the game, G wins the game, and the rewards are these, right? And as a result, it's better to go right in this game. So now assume at some iteration in the Q learning, we have this, and we saw that the QD right changed from 16 to 17 as expected. Why? Because going right is better in this case. This is training. So this was one iteration, for example, one tiny iteration of the Q learning, but we need a lot of iterations for that until convergence. Assume I train this, and all of the Q states actions are converged after training. Now in the test phase, what should I do after training? So I start from state D again, right? What do? I just choose the best action. At every state, I choose the best action. How do I do that? Argmax of QSA with respect to action, right? So when I'm at D, argmax of QD A with respect to A. What actions do I have? Right, left. So which one is larger? QD right or QD left? Of course, after this convergence, QD right becomes larger. Then I go right. Now I'm in state E. Argmax of Q, E, right and left. Right is larger, right? Goes right. Then we go to a state F again. We go right. We go to state G and we win the game. This is a test phase, right? Interesting. Okay. By the way, this is just one-dimensional random walk. We can have multi-dimensional random walk. And so I think we stopped here. Let me go deeper into this. So the Q function. So now we start this session. The Q function can be approximated by any linear and nonlinear function. Let's approximate this Q function. That's why we call it Q function. Okay. This Q can be approximated. Now you tell me the function which approximates the Q function can be linear or nonlinear. One of the best nonlinear functions which approximates functions or behaviors is what? Neural networks, right? So let's approximate it by a neural network with weights W, okay? The weights or parameters W. So now recall the temporal difference of Q function. Okay. Now we go in the mind of researchers in DeepMind. In what year? I don't remember. I think several years ago, maybe 2013, 14. Okay. At that time, they were a small company in UK. They were not in Google. Did you know that? Did you know that DeepMind was not in Google? They did some breakthrough in AI. Then Google bought them for millions of dollars, right? So this was their breakthrough. We go into their minds. What did they do? They said, okay, we have reinforcement learning. Let's propose deep reinforcement learning. How do they do that? They said, okay, we have Q, temporal difference in Q function, right? This is the function. Can we write it as an optimization in neural network? Do you see this? So basically, what is this delta? So this is the previous Q, this is the next Q. So it's like an optimization, similar, okay? This is my delta, right? In convergence, delta becomes almost 0, right? Agree? So I can see this as a loss function. This delta can be seen as a loss function. And as you see, this minus this, right? So I have this term minus this term. So let's use mean squared error between them, right? So mean squared error between this, so this, let me say this, 1, 2, here is 2, and here is 1, minus 1, right? And squared, and 1 over half, 1 over 2 is because the derivative becomes, so it's like x squared becomes 2x. I want to get rid of the 2 in the derivative, okay? Then I have this loss function. My Q, what is Q then? You tell me. The neural network tries to approximate Q. So QSA is the output of neural network. Okay, interesting. But, okay, they went and implemented that. They saw that it's not working. Why? Why did, as expected, it shouldn't work, but they didn't know at that time. First, they tried it, it didn't converge. They saw that it never converges. Then they had a meeting, right? Then they said, why isn't it working? Can you guess? Obviously. So we have this and we have this. When we want to minimize the distance between two things, in real life, it's like what? We have two persons. One person is chasing another person, right? When are we happy? When one person reaches another person, the distance becomes 0. Right? But the problem is that when you move person 1, person 2 also moves. Why? Because both of them have Q in it. In both persons, in both terms, we have Q. When you change the parameters of Q, so it's like one person is chasing another person, but the other person is also moving. They might not never reach each other. So as this is called the problem of moving targets. The target is moving here. So what should we do? There are two approaches to handle this. You tell me without looking. In real life, one person is chasing another person, and the next person is also moving. What do you do? What? So you're saying that slow down one of them and make the other one faster. The extreme case is stop one of them. So using chain or something, let one of them be fixed. Okay, the target be fixed. So as a result, they said, let's this be target, this part be target, and let's chain it down so it doesn't move. How do they do that? Let's use two networks rather than one network. Okay, so I have one network with parameters W, another network with parameters W bar. Okay, I call this network. So this is the network that approximates my Q estimation function, Q value estimate network. And this is called target network. Target network, okay? Then I have only one thing which changes. So it converges, hopefully. So its derivative becomes this. Do you agree? The derivative of this with respect to W becomes this. Note that here I have W bar. It's not a function of W anymore, right? And then I use this gradient descent. By the way, in the literature of deep learning, whenever I write one step of gradient descent, what does it mean? It means one step of backpropagation. Because backpropagation is nothing but gradient descent and chain rule, right? So when I say this, basically it's one step of gradient descent or one step of backpropagation. I mean one backpropagation from end to start, end layer to the start layer. Okay, so now this is what we have. Initialize W and W bar. Observe the current state S while not converged. What do I mean by converged? Because the loss function of neural network oscillates, right? It's going down, but it oscillates. Gradually, it stagnates and it becomes very low. That's convergence. Select and execute the action A, again, either epsilon greedy, right? Epsilon greedy. Observe the new state S prime, because whenever you do some action, the state of environment changes. Then update this. This is one step that it kind of does what temporal difference of Q learning does. Then go to the next state. There is one thing which needs discussion. Should we always keep that target network fixed? No, because if you always fix it, then this will not be equivalent to this, right? So let's relax the problem a little bit and update the target network every k times periodically. Agreed? So every k times update w bar. How do we do that? How do we do that? You tell me. So either you say, either you copy the weights of the target network to the Q values estimate network, okay, or you do one step of backpropagation in the target network. Okay, both can be done. Why am I allowed to copy that? Because those two networks, those two Q functions were supposed to be the same function. Okay, interesting. So another approach to resolve this issue is this. So the one approach was using two networks. One of them was target network. The other approach is that let's use one network, but let's capture or store the previous experiences in a buffer. What are the experiences in reinforcement learning? State, action, reward, next state, right? S-A, S prime, R. So let's because whatever we do in every iteration of reinforcement learning, we have these, let's store them. And after, so initially we don't have any previous experience. Initially train as before, but after a while you have stored enough previous experiences. Then from that step onwards, what do? You only get your mini batches for training from the previous experiences. Why do you do that? Why does it make sense? In this case, you will not have drastic changes of Q because you're using your previous log of history. We saw this behavior previously in this course. Where? Do you remember that? Mini batch. No. You remember momentum? I explained in both intuitively and mathematically why momentum reduces the amount of oscillation, because we're using the log of history. You remember? So in gradient descent, if we oscillate a lot, we're using momentum, we don't oscillate much. Likewise here, when we use the previous experience, we'll not have drastic changes. As a result, hopefully converge. But interestingly, using these, by the way, this approach is called experience replay. These two approaches do not have any theoretical guarantee for convergence, but they usually converge in practice. So you might not converge. Okay. There are two things in machine learning which are famous for being very hard to converge. Can you tell me? One of them is reinforcement learning, deep reinforcement learning. The other one is GAN, generative adversarial networks. They're also hard to converge. So yes.
Yeah.
I don't know which one is less likely to converge, but I know that they both, in practice, they have shown to work in practice usually, but they don't have any guarantee for convergence. By the way, because here we don't have any guarantee because the estimator of Q function, which is a neural network, is a nonlinear function. But if we approximate the Q function with a linear function, it has a theoretical guarantee for convergence. Okay. So the first paper which implemented gradient Q learning by a deep neural network, which we explained, was Deep Q Network, or DQ, and it was proposed in 2013 by DeepMind, and then Google bought them. This paper also is considered as the first algorithm in deep reinforcement learning. DRL is R. What is deep reinforcement learning? Nothing but reinforcement learning, plus the fact that because in reinforcement learning we have a bunch of things, right? Let's approximate these things by a function and let the function be a neural network. So for example, we have Q function, right? We have Q function. We have value function. We can have V We can approximate it by a value function. Policy function, we can approximate the policy pi with a function, right? If you approximate one or several of these by one or several neural networks, this becomes deep reinforcement learning. So when you want to learn deep reinforcement learning, you should learn reinforcement learning. It's nothing but that. Okay. So what did they do in deep Q network for experiments? How did they show how it is working well? You need to sell your algorithm, right? It's marketing. So what did they do? They trained that DQN on the Atari games. You remember Atari games? Good time. Atari, Sega. So we have frame at time t as input state, right? And then, so we have convolutional neural networks. Why? Because we have frame image as input. And then we have a bunch of fully connected networks, layers, fully connected layers. We have to have at least one fully connected layer. Why? Because we want to reshape it. So the output layer should have the number of neurons as a number of actions. What are the actions? By the way, so assume the joystick. So these are the actions on the joystick of the Atari. Or if it is PlayStation, these are the actions or the buttons on the PlayStation console, right? So we have these actions, and you tell me. So we have these amount of neurons at the end. What activation function am I using at the end? It's a classification problem, right? So assume, I think, you tell me what activation function works well here?
Binary.
No, it's not binary. So how many classes are there? I don't know. Maybe 20, right? So softmax, right? Because we wanna, so it becomes like a probability, right? So for example, it becomes like this. What does it mean? This action has the largest probability to do. So basically it says that for this frame, it's best to do this action, right? Okay. Interestingly, they could outperform humans in playing Atari games. Policy gradient is the other action, the other algorithm for reinforcement learning. So I told you that for Markov decision process, we have value iteration and policy iteration. For reinforcement learning, we have Q learning and policy gradient. So Q learning was a model-free, value-based method, right? But policy gradient is a model-free, policy-based method. Okay. In Q learning, do you remember? We learned the Q function, right? Explicitly. But when we never learned the policy explicitly, the policy was implicit. Why? For finding out the policy, we always use argmax of Q with respect to action, right? But in policy gradient, it's the other way around. We learn the policy explicitly, but we learn the value or the Q, whatever, or reward implicitly. So both of them, by the way, try to find the best map of policy, optimal policy. It's always the goal of reinforcement learning. The policy gradient attempts to learn the policy function explicitly, as I said. So now you tell me, do you remember the policy can be a stochastic or deterministic? If it is a stochastic, it is a conditional distribution of action with this conditioned on state. But if it is deterministic, then it's a function, pi s. Each of these policy functions have pros and cons, right? So usually the deterministic function is a discrete function, usually, not always. But a stochastic policy is usually continuous because it's like a probability density function, PDF. So it's a smooth and continuous. So it's good for optimization, right? Also, it's good if the action space is continuous. But in general, even for a stochastic policy, we can have discrete stochastic policy or continuous stochastic policy. What is a good option for discrete stochastic policy? So I have a bunch of values, discrete values. I want them to behave like probability, but a Gaussian probability. What should I do? If I want them to behave like a probability, I just divide each of them by sum of them, right? So they will be between 0 and 1, and they sum to 1. But if I want them to behave like a Gaussian probability, then what should we do? What? No, we already normalized that. But I'm saying that we should tweak it a bit. We should put them in exponential operator, right? Because Gaussian distribution has exp in it, exponential. So when we do that, it's called softmax, right? This is softmax form. This is for discrete ones. But if it is already continuous, we can use normal distribution, Gaussian distribution, right? They both have almost, so this one has almost Gaussian distribution, this has exact Gaussian distribution with mean and covariance of which are functions of the state, right? Now consider, so let's compare supervised learning and reinforcement learning. In supervised learning, we have labels, right? We have labels. So assume I have gathered data and I know that for every state, what is the best action to do? For example, by professionals tell me that in this state, the best thing to do is this, right? So I have pairs of the state and best action. As you see, action has a star in it. So it's optimal action. So my labels, my data becomes a state. My labels are actions, best actions, right? So it's supervised learning. Then what can I do? It's like a regression problem or classification problem, whatever you call it. So you can use any loss function for supervised learning, such as, do you agree that, what is this? This is a stochastic policy, right? Of A star given Sn, right? The best action given state, right? Then so it's like a likelihood, whatever you call it. This is log likelihood, right? By the way, I'm not sure whether I told you this in this course, but I think I said. Why do we use log likelihood other than likelihood in machine learning a lot? There are at least 3 reasons, 2 to 3 reasons. Can you guess?
Not like maximizing the log likelihood, same as maximizing.
So you are saying that this explains why it is justified theoretically. This is correct, valid theoretically, because logarithm is a monotonic function, right? So when you maximize something, you can also maximize its logarithm, right? So their argmax will be the same. But I'm saying that, why do they do that? So let me tell you. First off, usually likelihoods are probabilities, right? Probability distributions. And usually we use Gaussian distribution or something similar to the Gaussian distribution. And Gaussian distribution has exponential operator in it. So many probability distributions are in the exponential family. One of them is Gaussian. And why do we use Gaussian distribution? Because this is the most common distribution in the world, continuous distribution in the world. And why? It's because of the central limit theorem. Central limit theorem says that when you have a bunch of data, which can be even from different distributions, but when you add them up, when the number of samples goes to infinity, the distribution of the total thing becomes like a Gaussian distribution. And in physics, in real world, we usually have addition of things, right? That's why Gaussian distribution is the most common distribution in the world. Even the cells in our eyes are Gabor filters, which have Gaussian distribution. Now, so we use Gaussian distribution or exponential family. So EXP is a pain in the neck. Let's get rid of that. Let's use the opposite operator, which is logarithm. This is one reason. The other reason is when the data are IID, independent and identically distributed, what happens? What is the joint distribution? Becomes the multiplication of distribution of each of them, right? Multiplication is a pain in the neck. Summation is easier. How do we convert multiplication to summation? Log. Logarithm of AB is logarithm of A plus logarithm of B. So logarithm of multiplication becomes summation of logarithms. The third reason maybe is that when something becomes very large, logarithm dampens it. Doesn't become too large. Anyways, so we use logarithm of this, log, and the summation of them over n, right? This was basically logarithm of multiplication, which became summation of logarithms. Then argmax of that with respect to w. It gives me w star, right? How can I maximize this? I can use gradient ascent, right? So I take derivative of this term, and this is plus because I'm using gradient ascent, right? Okay. Now, in reinforcement learning, rather than pairs of a state optimal action, what do we have? Do we have optimal action in reinforcement learning? We don't have optimal action, right? Otherwise, the problem would be solved, right? So what we have as a data, training data in reinforcement learning is a state action reward. Because in reinforcement learning is nothing but interacting with the environment. So I have a state, I do some action, I get some reward. So state is S1, A1, R1. Note that there is no star on action because there is no optimal action yet, right? So we can say, let's maximize the total discounted reward now, right? In other words, we can, in another way to do that is this. So we have this similar to, compare these two, very similar. The only difference is this term. You see this term? Do you see this term? Let's come here. So this was supervised learning. This is reinforcement learning. This term is different. Can you tell me what is happening here? Why are we putting this term here? By the way, note that here I have a star. Here I don't have a star. Okay. Exactly. So thank you for your answer. So basically, let me rephrase what you said. Here, I have the best action in supervised learning. I have the best action, so I trust it and I use it in gradient ascent with peace of mind. But in reinforcement learning, who says that I should maximize this? Maybe for this state Sn, action An was awful. Why should I maximize that? I should maximize it only when its total discounted reward is large. If the action An is awful for state Sn, its total discounted reward Gn becomes very low, very small, so it kind of ignores that in gradient ascent. Did you get it? So we are scaling that. Interesting. Now we see this algorithm, reinforced algorithm. This was one of the very first algorithms in RL, proposed in 1992. Rumors say that this is the first RL algorithm. By the way, why is it all capital? Yes, because these are starting letters of a bunch of words which became reinforced. So okay, so they intentionally use the words so it becomes that their shorthand becomes reinforced. Anyway, so reinforced algorithm is a policy gradient algorithm that I just talked about. One of the policy gradient algorithms, and it uses temporal update in equation 34. Okay, I think equation 34 was this. Yeah, what we just talked about. So what does it do? It plays the game or interacts with the environment for multiple times. Okay, every time that the game is completely played once is called episode. So assume you have chess, you play it over and over again. Once you win, once you lose, etc. Right? Or once you have draw. So you have episodes. Every episode has T steps, where T might differ in different episodes. Do you agree? The episodes might not have the same length. In this algorithm, alpha is the learning rate. So let's see the algorithm. Initialize W, your parameters. Observe the current state S. And for each episode, what do? Play the episode from start to end. So you have a bunch of triplets. S0, A0, R0, then S1, A1, R1, until ST, AT, RT, right? So basically, it's one tiny trajectory in the whole tree of possibilities, right? At every episode. Then what do? By the way, I have made a mistake here. This must go inside the for loop. Okay, what do I mean? Then for the whole episode, what do? Calculate the total discounted reward in the horizon, but we have a bunch of total discounted rewards. What do I mean? I have G0 for the whole horizon. Then I go to the next time slot, T1. Then I have G1 for the rest of the horizon. Then G2 for the rest of the horizon. Okay, that's it. Then for each of them, I update my parameters. Here is one step of gradient ascent. You can see it as one step of gradient descent if you use minus, right? Right, agree. One step of gradient descent is equivalent to one step of backpropagation. So you can use it in neural network too. At that time, we didn't have deep neural network. We had multi-layer perceptron, but we didn't have deep neural network. But whatever in the ancient times you could do with gradient descent, now you can do it with deep neural networks as well, right? So you can do it. And now let's analyze it a bit. Assume I play chess in different episodes. In one episode, I play awful from start to end. Then what happens? All of my GNs, my G0 until GT, become very small. So in all of the gradient ascent steps, they almost are all ignored, right? Because of this GN. Because of this GN, they all become ignored. Because I played awful, why should I update my W? Now assume I play very well in this episode. All of these steps, their G's, G0 until GT become large. So they all update W. Now what if I play good until the middle, but in the middle, but when I say I mean machine, right? The machine plays good until the middle, but from the middle until the end, it plays bad. What happens? What happens to G0? G0 has the effect of 0 until T. Z until T over 2 was good. T over 2 until T was bad. So G0 will still be a bit good because of this part. But T over 2 plus 1 is very bad. So for this part, it will be ignored. For this part, it will be almost ignored, not much. But this G0 is less than the G0 of very good play. This G0 very good play will be very larger than this G0. Agreed? Did you understand? Okay. Now, let's go to the fun part, AlphaGo. So whenever, especially Google, does some breakthrough in games or etc., they call it alpha something. So AlphaGo is for the playing Go game with artificial intelligence. We also have AlphaFold, for example, for use of artificial intelligence for DNA folding, right? Gene folding. So AlphaGo is a game of Go by reinforcement learning. And they usually publish these papers in Nature, okay? So game of Go, what is that? It's an Asian originated East Asia game where two players alternate to place a stone on a vacant or empty intersection dot. What do I mean? We have a board. The board is 19 by 19, okay? And you have a bunch of dots. Do you see these dots? These dots are called intersections also. Initially, all of the dots are empty or vacant. Then what happens? Then you have two players, one player with white stones, the other player with black stones, and they put stones on the dots. Then connected stones which have no adjacent vacant intersection are removed. These are the rules of the game. I'm not an expert in this game. You can Google the rules of this game. There are some YouTube videos on the rules of this game as well. Then, by the way, it's a hard game. It's not an easy game. The player who controls the largest intersections at the end of the game becomes the winner. Okay. So basically, as far as I have seen, apparently, when you put it in some way, you can remove the stones of the opponents from the board. But at the end, the player with the most number of stones on the board will win the game. As this is what I understood from the game. Okay. So this game is 19 by 19. It's board, right? So how many dots do we have? 361. In every dot has three states, possible states: empty, white stone, black stone. So how many possibilities or states do we have? The state space has 3 to the power 361 possibilities. It's large, very large, right? I think it's harder than chess. No, I'm not sure about that because chess has more pieces. Anyways, so AlphaGo, what was proposed in 2016, it uses deep reinforcement learning for playing the game of Go. Let's see what they did. They have several networks. Let's go one by one. AlphaGo has a policy network for modeling this pi of A given S. Okay, where the input of the network is the state S, and S is the configuration of the board. So let me say it in this. We have policy network. We also have a value network. I will introduce value network later. Policy network, from its name, is obvious. What does it do? It predicts the policy. It tells you what action to do, right? So its input is, as always, a state. What is the state in this game of Go? The configuration of the board configuration, right? And your output is the action. So the output of the network is a distribution of actions. What do I mean? Of course, they use softmax activation function at the end. And it is a 2D neural, it's like a 2D neural network at the end, 2D layer, right? So you have a bunch of neurons with different probabilities, right? So if it is larger, this says if one of the dots will have larger probability, right? After softmax. What does it mean? It means put the next stone there. Okay. Because either the computer is white stone or black stone, so it knows its color. Then it tells that, hey, computer, put your stone of your own color on that dot. Okay, interesting. How did they train it? They trained it in 2 ways. First, they used supervised learning. You remember we talked about supervised learning. So how do they have the data? Of course, they have states, the configuration of boards, and the actions played by the professionals. So they use 30 million board configurations. It's not large. It's not too many. Why? Because it's much less than this amount of possibilities. 3 to the power 361. But this is the best that they could do. 30 million board configurations played by professionals. Pairs of states actions. Then they maximize this log likelihood. Basically, what are they doing? This is gradient ascent, but they are using gradient descent by using minus rather than plus, right? So they are minimizing the negative log likelihood rather than maximizing the log likelihood. Okay. Then after this, they fine-tune. They fine-tune the policy network. How do they do that? They say, let's use policy gradient. Right? So they use both supervised learning and reinforcement learning. So they use policy gradients. Policy gradient. In the policy gradient, what do they do? Do you remember the policy gradient was this? It had this part in it. Do you remember? For scaling the gradient, if it was a good action, this is large. If it is a bad action, this is a small, and it ignores that, right? But GN, do you remember it was the total discounted reward? But here, GN, they simplified that. By the way, let me tell you how they are using. So here we don't have the board configurations and the best actions. I mean, the best actions of board configurations played by the professionals. So what do? They have the policy network trained until here, until this slide, right? Then they say, hey, policy network, play against yourself. Play against yourself. So once you play against yourself in the previous iteration, so what do I mean? Once it plays against itself, then I update my policy network by this game, by this plane, by this episode, I mean. Then I have two versions of my policy network. My current policy network and my previous policy network, right? So it always plays against its previous version. Hopefully, the next version is better than the previous version. And they played again and again for this, right? So against its previous version, fine-tuned in the previous episode, right? Every time it wins against its previous version, they let GN be 1. But if it loses or if it is a draw, it becomes -1. Right? Agree? Then, so they simplified GN. Now, they have another network, and that's value network. What does it do? It predicts the value VS. What does it say? So S is the state, it's the board configuration as input of this neural network. The neural network tries to approximate the value. So its output is value, and the value is the best reward for that state, right? So basically, what does it mean? How good my board configuration, how good my state in this configuration it is. Why do we need that? Can you tell me? Because the machine needs to find out whether it's in a good situation or not, whether it's losing or winning. Okay. So the previous policy network was for finding out what to do. The value network is for finding out how good the situation is. Okay. Why is it required? Can you tell me? Have you seen games like chess, professional chess matches? They never end. One of them either resigns or they will say, okay, it's draw. They never end. So sometimes the network finds out that it's losing, so it resigns. Why this? If VS is very low, it means that I'm losing. So why do I bother continuing? Let me resume. Sometimes the network sees that it's losing, so it offers a draw. The other player might reject it, right? But so for offering draw or for resigning, we need the value network. So yeah, as I said, how do they train it? The value network is trained by gradient value learning. So basically the data for training are S and G, where G is this. G is 1 if it wins. If it loses, again, it's -1. Or if it is draw, -1. Then this is my loss function. What does it mean? This is my value, output of the predicted value, output of the neural network. And G is when I win or lose. So basically it says play an episode. If you win, then the output of network should be 1. If you lose, the output of network should be almost 0. By the way, this is a continuous output. So it's what is the output of this value network? You tell me. It's between 0 and 1, right? So what activation function did they use? It's a 1 neuron, by the way. 1 neuron at the end, right? 1 neuron. It's a regression problem, right? They are using mean squared error, last function. And the output of neural network is between 0 and 1. So what activation function did they use? Sigmoid activation function, right? And the target, the label is 1 or -1. Hard. By the way, sorry, I apologize. They are not using between. So it's between -1 and 1. I apologize. Anyways, rather than between 0 and 1, is between -1 and 1 because the labels, the target labels are 1 and -1. But now let me change my word. What activation function are they using? One neuron at the end. What activation function is between -1 and 1? No, sigmoid is between 0 and 1. What? Sine? No, sine is not continuous. We usually use continuous. The tan edge, hyperbolic tangent, is between -1 and 2. So then they minimize it by, so this is one step of gradient descent, which is one step of back propagation, right? So AlphaGo, then AlphaGo combines the two networks into a Monte Carlo tree search or MCTS algorithm. What is Monte Carlo tree search? Let me tell you with this example. So consider the tic-tac-toe. Okay. The tic-tac-toe game is this. Then how many cases do I have? You tell me. Either I put my star here, I put here until I put here. How many? 9. 9 cases. Agree. Then it's the turn of circle. How many cases do I have here? You tell me. So it's here, circle here until circle here. How many cases? 8. Again for this, 8. Again for this, 8 cases. Then again for this, you tell me. This one until what this is 7, etc. Right? So, but this becomes large, especially if you have too many states, right? So the whole tree is very large. Then what do? They say, okay, it blows up the memory, and also the time complexity is awful if you want to search the whole thing. Of course, if it is you don't have too many cases, you can go and search in the whole tree and see which one is the best, so you do that, right? But they say, let's not grow the tree in the whole possibilities and scenarios. Let's only go into the cases where I know that they are most probable to win or something, right? So the best, there are some specific paths which are the best. So I grow the tree only in some specific paths. This is called Monte Carlo tree search. And this is a family of algorithms. There can be a course on that. Okay. You can see reference 11 as a survey on that. It's out of the scope of this course. So every node in this MCTS, as I said, is a state S. Every edge is an action. Do you remember? Here, every node was state and every edge was an action. Interesting. Okay. Now, every possible episode of game is one of the, do you agree? Every episode of the game is one trajectory in the tree and its own and it has its own reward. Agree? As a tree becomes very large, it is memory error. You will get a memory error, and so you need to do MCTS. By the way, this MCTS is usually used in different games for solved by artificial intelligence, such as AlphaGo, AlphaZero, which has been proposed for chess and shogi. What is shogi? It's Japanese chess. Okay. All of these usually use MCTS. I think a stockfish, am I right? A stockfish, sorry. The stockfish is the most powerful engine for chess. It uses MCTS, okay? The acknowledgement, some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo Department of Statistics. Also watch teachings of Professor Pascal Poupart. He has good videos on YouTube about reinforcement learning. A good textbook in reinforcement learning is by Richard Sutton. You know Richard Sutton? He's the most famous scientist in reinforcement learning. He's in University of Alberta. I think he has retired. And these are the references. Any question? No? Let's have a break, if you agree, and come back. How much break do you need? There are only, I don't know how much you say, you guys. How much? A quarter? Okay, so let's come back at 8:25 is good? 8:25, okay, thank you. Okay, now we go to the next topic, which is generative adversarial networks, or GAN. How much do you guys know GAN?
The networks competing against each other.
Yeah, do you know that? No? Okay. So let's go into that. So suppose we have a generative model which takes a random noise as input and generates a data point. What? Generative models in machine learning are like this. They get a noise and they output some real world, some data. Assume I want to train a generative model on this class. And assume my input noise is one-dimensional. What happens then? So I randomly select this out of this distribution. Then I feed it to my generative model. It brings then here gives another person. Here gives another person. So everything corresponds to some noise, right? This is generative model. We have a bunch of generative models, such as variational autoencoders, such as adversarial networks and adversarial autoencoders, such as diffusion model. Okay. So now you tell me, I wanna have some generative model. It generates some data. The data might be image, okay, such as facial images. I want to see how good these are, right? Who is the best? What is the best judgment? Without looking at the slide, what is the best judgment for what?
Right now,
Humans' eyes, right? Humans' visual system, because we are generating them for human. If we were generating them for dogs, the best judges were dogs, right? So the best judgment is human, but we know that everything in machine learning is optimization, right? So we need to, and in optimization, we need to take derivative. Can we take derivative of humans' judgment? No. So we should replace it with something which we can take derivative, right? So now we are in the head of Ian Goodfellow, okay? At the time when he was a PhD student of Yashua Benjo in University de Montreal. He said, okay, I can't take derivative of humans' judgment, so let me have some classifier for the telling me, for judging, for telling me whether it's a good generated image or not, right? A classifier or a discriminator. So then it's a good idea, but he went a step further. He said, why do I use a pre-trained classifier? Let me train the classifier at the same time that I'm training the generative model. So let me train them simultaneously, okay? Simultaneous. Train them simultaneously rather than using a pre-trained network, right? And how do they do this? So they are enemies of each other. Why? Because generative model wants to fool the judge, the classifier, right? And the classifier wants to discriminate between the fake generated data and the real data. Okay, did you get it? Did you get it? So as a result, they compete with each other, and we know that in competitions, what happens? People get better and better because one of them wants to get better than the other one, so it tries further, right? So they compete with each other and they gradually become stronger by this competition, right? Each of them. This is called generative adversarial network, GAN. Why? Because they are adversarial to each other. They are enemies of each other. It was proposed in 2014. Okay, by Ian Goodfellow et al. So, by the way, the word adversarial has two use cases in machine learning. One of them is adversarial learning, which I just said, okay, used in generative adversarial network, or GAN, in generative models, right? The other one is adversarial attack. It's different. What is adversarial attack? Do you know that? So it's a field of machine learning and signal processing. What does it do? Do you agree that assume I train a neural network on image data or humans, not humans, sorry, animals, okay? It is a classifier for animals, dog, cat, etc. Then in the test phase, I give a dog to it. It says that it is a dog, right? Now I want to change the input very slightly, that using a human's visual system, it is not detectable. You cannot find out this change. But by this tiny change, I ruin the whole network. Okay. So I want to attack this network, kind of hack. I want to hack it. So it's against security, right? So I want to attack this in a way that it gets ruined. And then by this changing some pixels in this input image, it says it's an elephant. For a dog pixel, it says it's an elephant. How do I find which pixels should I change? Which are the best pixels to change? These are adversarial attack. And so it has two mainstreams: adversarial attack and how to protect against adversarial attack. So it's a security thing, right?
Be like a pro for security, like if you don't want people like taking names and images of like Facebook or LinkedIn, right?
Okay.
It's a good way to like mask people's identities from machine.
As masking things inside the signal, you mean? So for example,
Cases that like names.
So what you're saying that you encapsulate the information of name inside the image, for example, you are stuck. So that's another thing. That's called watermarking.
No, like I'm saying it's like a good security measure.
Yeah. So you can make in adversarial attack, you can make your network robust to adversarial attack. Okay.
Yeah.
You can make it robust. Yeah, exactly. So you can propose algorithms for attacks, and you can propose algorithms for defenses against attacks. So there are two different things. Don't confuse them, okay? Adversarial learning. So adversarial GAN. Now, in the original GAN, it is also called vanilla GAN. It was proposed in 2014. Consider n data points, and these data points can be images, right? X1 to Xn. So we have a generator G and a discriminator D, right? By the way, please interrupt me whenever you don't understand. I don't know whether you are understanding or not. Please let me know. So my noise is Z, p-dimensional, and my data is X, d-dimensional. Usually P is much less than D. If it is image data, D is the number of pixels, okay? Then my generator gets Z as input, outputs X. But this output X is a fake data. We also have real data X, right? Okay. So G is a map from Z to X. Now, I want to have a classifier or discriminator, also called critic, right? Which gets X as input, but outputs some score between 0 and 1, saying whether it's real or not. If it's real, it says 1. If it is fake, it says it's 0. Okay. For training D, what should I do? Of course, for training, I know what is real, what is fake, right? For training, I should use this 1 and 0. What output of them? D will be a float value between 0 and 1. So it gives you a score, a probability of whether it's real or fake. So as a result, it has 1 neuron at the end. With which activation function? Which activation function gives you values between 0 and 1 and for 1 neuron? Sigmoid, right? So we use sigmoid for them. And now you tell me, if D is working very well, for real data, it gives you a score close to 1. And for fake data, it gives you a score close to 0, right? Now, okay. The discriminator, as I said, can be a pre-trained classifier, agree? But let's train classifier, discriminator, and generator at the same time simultaneously. Why not? While we are training the generator. So they become stronger and stronger by competition. Okay. Generator tries to generate realistic points to fool the discriminator. So it gives it a hard time to distinguish a generated point from a real point. Agreed? On the other hand, discriminator tries to discriminate the fake or generated data from the real data. When I say fake, I mean generated data. Okay. So as you see, we have an adversarial game between them. So it's a game in game theory, right? And it's a zero-sum game. What do I mean by zero-sum game? So in game, every player has some payoff or benefits. Of course, every player wants to maximize its own payoff, right? If one player gets the whole benefit, and if in this case the payoff of the other player becomes 0, it's a zero-sum game. In other words, the summation of the benefits of the two players is the whole payoff. So player 1, player 2, either they get half-half, or player 1 gets everything, player 2 nothing, or player 2 gets everything and player 1 nothing, right? In this case, it's a zero-sum game. Consider a cake. We want to divide it between us. If I take the whole cake, you will get nothing. It's a 0. But consider a magic cake. If I take the whole cake, something still remains for you. This is not a zero-sum game. Okay. By the way, for more information on game theory, see my YouTube channel. In the adaptive and cooperative algorithms course, I have explained game theory. Interesting. So Ian Goodfellow, by proposing GAN, brought game theory in machine learning. Okay. Now, let's go into the mathematics. So we denote the probability distributions of the data set and noise by P data and PZ. So P data X is the probability distribution of data, right? The data set, real data. PZZ is the probability distribution of noise. Usually it's Gaussian noise. Okay, agreed? The discriminator is trained by real points from data set, right? As well as generated points from the generator. Do you agree? Because the discriminator for training that, I need both real data and fake data. Real data comes from the data set. Fake data comes from the output of generator. But the generator, for training that, I need noise and fake data, generated fake data, right? I'll tell you what it means. Okay, so we are training them simultaneously. As a result, I have one loss function for both. Okay, so let's see this. This is the loss function that I'm having. Let's analyze it. So it has two terms, this term and this term. VDG. Why do we call it V? Because it's also called value function of the game. It's a function of both discriminator and generator. Here, when I say D, maximize with respect to D, I mean with respect to the weights of the discriminator. Minimize with respect to G, I mean minimize with respect to the weights of the generator function. What do I mean? Basically, this loss function is maximized by the discriminator, minimized by the generator. So far clear? Okay. By the way, when I say maximize something by a neural network, I mean minimize minus that thing in that neural network. Because in neural networks, we usually minimize things, right? And here, E is an expectation. By the way, you shouldn't panic when you see expectation, because you can always approximate expectation by Monte Carlo approximation, by approximated by average over the batch, mini batch. Do you remember? Okay. So now, this is the structure of the GAN. I will explain the loss function in a few seconds. Just give me a second. I have the loss, the noise. I feed it to the generator. It gives me generated data, X. Why is it this length is smaller than this length? Because usually the dimensionality of Z, which is P, is much less than D. Okay. Do you agree that this length should be equal to this length? Because both are the dimensionalities of data, right? This is one neuron. One neuron. Agreed? With sigmoid activation function. This is P. I feed noise to generator. It gives me fake data whose distribution is PGX. Note that this is different from P data X. I hope the generator hopes that PGX becomes close to P data X. This is the desire of generator, right? X from the data set is from P data X. So for real data and the fake data, I train it by the discriminator. I train the discriminator by them. So far clear. So this structure is clear. Now let's go back. By the way, we use Monte Carlo approximation for expectation, right? Over the mini batch. Let's go back to the loss. Let's analyze it. Have I said it here? Yes. Okay. You tell me. Consider first discriminator. Please focus here because I want to ask you. Discriminator. Discriminator wants to maximize this. Do both terms have D in it? Right? So both terms matter for the discriminator, right? Agree? So let's consider the first term. Maximizing this. What is this? Maximizing expectation of something roughly means maximize inside the argument. Maximize log of something. What does it mean? Logarithm is a monotonic function. So basically it means maximize inside the logarithm. So basically D wants to maximize D of X. Why? For what is expectation over? You tell me. Real data. With respect to real data, right? So the first term is with respect to real data. The second term is with respect to noise. Okay, so far clear? For real data, my D wants to maximize D of X. Obviously, because of this. Where was that? Because of this. For real data, it should output 1. Its maximum is 1, right? So term 1 for the discriminator makes sense, right? Now term 2. Discriminator wants to maximize this term 2. So maximize expectation roughly means that maximize the inside the expectation. So logarithm is a monotonic function. Basically, it means that maximize inside the logarithm. Maximize 1 minus dgz. What is dgz? Means that. What is gz? Z is the noise. You input it to the generator. Gz is the output of the generator. So it's a fake data. Gz is a fake data. You feed it as input to the discriminator, right? What should the discriminator give you? What is in the eye of discriminator? In the eye of discriminator, the discriminator should, for the fake data, what should it give you? It give you 0, right? So let's see if it makes sense or not. My D wants to maximize the second term. So it wants to maximize the logarithm of this. So wants to maximize 1 minus dg of z. So wants to maximize minus dg of z, because 1 is a constant, right? Agreed? Maximize minus something is equivalent to minimize that thing. So it wants to minimize d of g of z. Of course, makes sense, because d of g of z should become 0 in the eye of discriminator. Agreed? Agreed? So both terms make sense for the discriminator. Now let's go to the generator. The first term, is it a function of generator? The first. So it's a constant, goes away. We don't care. Why? Because the arg mean is important to me. Arg mean in neural network is weights, not the mean value. If the mean value is important, I need to add back the constant at the end, right? I simply can drop it completely because argument of the optimization is important to me. Do you understand what I'm saying? Do you also understand? Okay. No? Yeah. Okay. So the second term, then you tell me. So minimize this. Let me clear this part. Minimize that second term. Minimize for G, right? It roughly means minimize inside the expectation. Logarithm is a monotonic function, so it means minimize inside the logarithm. Minimize 1 minus d of g of z. 1 is constant. Basically means minimize minus dg of z, right? Minimize minus something is equivalent to maximize that thing. So maximize this, obviously, because generator is enemy of discriminator. So it wants it to output 1 for the fake data. Very beautiful, right? Makes sense. Now you might be wondering, why do we have 1 here? What's the point of this one? Because d of g of z is between 0 and 1. 1 minus that is the opposite of that. It's between 0 and 1. Right? Interesting. So the loss function makes sense. Okay. This is minimum, maximum. It's a minimax optimization problem. When we have minimum, maximum of something, it's a minimax optimization problem. If it is maximum, minimum something, it's maximin optimization problem. It's a famous optimization problem in game theory. Okay. What game does it show in the world of mathematics? In the real world, someone is maximizing something, the other person is minimizing something. This is between two people, right? It can be between several people. One person maximizes something, a bunch of others minimize that thing. What is that in the real world life? It's ganging up on someone. Bullying or ganging up on someone, right? This is the game of bullying or the game of ganging up. We have a bunch of bullies who come to a small kid, right? So you can see they are enemies of each other. the ganging up optimization problem. For more information, see my YouTube channel on that game theory course, right? And this is an alternating optimization problem. Why? Because we alternate between them. Maximize with respect to one of them, minimize with respect to the other one. Right? So we optimize over D and G iteratively until convergence of both of them. And the convergence is a Nash equilibrium. What is Nash equilibrium? I'll tell you. So we have two different types of equilibria in game theory, at least two important ones. One of them is dominant strategy equilibrium. Again, for more information, see my YouTube channel. One of them is dominant strategy equilibrium. Dominant strategy equilibrium says, everyone wants to maximize the payoff of itself only, selfishly. Nash came, John Nash was a mathematician, said, no, who says that? Let everyone maximize its own payoff and also maximize the payoff of the whole group. In other words, in the Nash equilibrium, no one wants to deviate anymore from its own state. Everyone will say, I'm good. I'm good. Do you see that? Do you see what I'm saying? In dominant strategy equilibrium, one might say, I want to deviate. I have a better solution. But in Nash equilibrium, everyone is happy with what they have. Okay. Have you seen the movie of A Beautiful Mind? Have you seen that? So for Nash equilibrium, there is a very good movie scene in that movie where it explains Nash equilibrium very well. Feel free to watch the video and focus on the part of the bar scene in the movie, where, briefly, let me tell you that a bunch of girls come to the bar, and Nash and his friends are in the bar. Then one of the girls is very hot, and then the boys are saying that let's go after and get the girl, the hot girl. So what is this? This is the dominant strategy equilibrium. Everyone wants the best, right? And suddenly Nash tells them, this is not the best strategy. Why? Because we'll go after the hot girl. What happens? The hot girl will reject all of us, right? Then we'll say, okay, so we'll go after the other girls, her friends, but they will also reject us. Why? Because they are second choice. No, not any girl wants to be the second choice. So they will reject. And at the end of the night, we'll have no girl. We all lose. This is not the best strategy. So Nash says, let's all of us ignore the hot girl and go after all of the other girls. They will accept us because they are not the second choice anymore. And all of us are happy with what we have because we all have, each of us has a girl, doesn't want to deviate. Do you see the difference between this simple idea? Revolutionized finance. For 100 years, dominant strategy equilibrium was proposed by Adam Smith. And then Nash completely changed finance. That's why he won the Nobel Prize of Finance. So consider Meta and Google. They are duopoly, assume, and they are competing with each other. If anyone wants to think of itself, there will be a war. Nothing will be good in finance. What they say, let us have an equilibrium where both of us are happy. Okay, so where were we? Yeah, now this is Nash equilibrium between D and G. Okay, we'll see that. So the original GAN uses a step of stochastic gradient descent for updates of each variable. So basically one step of backpropagation. So far clear? So D uses gradient ascent, or otherwise, or in other words, minimize minus the loss function. All right? You can write plus as minus minus. And generator use gradient descent. And they use minibatch, okay? So, by the way, this original paper also suggests that equation 4, this one, can be performed for several times before performing equation 5. That's fine. The important thing is that they are iterative. They're alternating between each other. Note that here, consider this is important. Here, I'm using dk, the previous discriminator, okay? Here, it is d because this is my optimization variable. But I'm using the previous generator as well, g, okay? And this gives me the next d, dk plus 1, agreed? Now, I use this dk plus 1 here, dk plus. G is the optimization variable, and g, k previous g. So far clear? So they alternate. This is called alternating optimization. For more information, this is a distributed optimization algorithm. For more information, see my optimization course on YouTube. Okay. I got a bit tired. Another way to solve this is simultaneous optimization, in which equations 4 and 5 are performed at the same time, not one after the other one. Okay. Let's talk about minimax versus maximin. So here is mean G, max D. Can we say max D mean G? Again, note that in both of them, we are minimizing with respect to G and maximizing with respect to D, but we are changing the order. In other words, let's change the order of these two. Are they equivalent? Yes. There is a proof. For more information, see this reference, I guess. This is a book in game theory. Okay. What?
Simultaneous optimization with formula be different because
so no, the formula is this. By simultaneous optimization, I mean use dk rather than dk plus. Okay. They are equivalent. So minimax and maximin are equivalent under some conditions. If there are two players and it's a zero-sum game, it is called minimax theorem. And here it is two-player game, it's a zero-sum game. So we don't care whether it's minimax or maximum. By the way, you know the difference of these two? In one of them tries to maximize its payoff, the other one bullies it. In the other one, the person first bullies that, and whatever remains, the other person wants to maximize it. So one of them first maximizes, then the other one damages that. In the other one, the bully damages that, then the other person tries to restore whatever they have. Okay. Network structure of GAN. So we can have deep neural networks for generator and discriminator. Where were we? By the way, so what do they do? The first layer of discriminator network is a d-dimensional, agreed? And it can be, if it is not image, then the discriminator is a convolutional neural network, right? They use max out activation function in the original GAN, but later they changed it. And sigmoid activation function at the end. For generator network, its input is p-dimensional and output is d-dimensional. If it is an image, the output should be like an image, right? It can be a vector reshaped to an image or convolutional layer. That doesn't matter. And so they use ReLU activation function and the sigmoid activation function, a combination of both of them. And the space of noise is also called latent space or latent factor. Okay. You know why? In generative models, we have you can see this as this graphical model where X is conditioned or caused by Z. So it's data which is observed. This is latent noise or latent factor. You see that in metaphysics of philosophy a lot. Metaphysics, not supernatural, is a subset of metaphysics. I'm not necessarily talking about supernatural. So whatever we see in this world, there is a latent factor for it. We have observed things, but there might be latent factors for it. You see this structure a lot in psychoanalysis. Your dreams have some meaning, right? Not, I mean, I'm not talking about the people who see, what are they called in English? I'm not talking about, I mean, scientific meaning. They have scientific meanings. Dreams have scientific meaning. Your mistakes in saying things has meaning in psychoanalysis. Freud says that. Freud talks about these things a lot. So everything in psychoanalysis has some latent factor. Then we train them by backpropagation. Where were we? Okay. Now, optimal solution of GAN theorem. So for a fixed generator, now let's analyze GAN theoretically. For a fixed generator G, what is the optimal discriminator? It's this. First off, let's see if it makes sense or not, and then we go to the proof. Does it make sense? You tell me. So D star is this for a fixed G. Okay. Let me remember. Okay. If P, it makes sense. Why? The best G, the best generator outputs some very good data, right? Fake data. When the fake data is very good, PG of X is almost P data X, right? Agree? For a very good generator, PGX is almost equal to P data X. Set PGX to P data X. What does it become? P data over P data plus P data. That's half. What was the output of D between 0 and 1? 1 means real, 0 means fake. When it outputs half, what does it mean? It's completely confused. For a very perfect generator, the discriminator becomes confused. Makes sense. Right? Now let's see the proof. This was V, right? And I'm using integral as the definition of expectation in the continuous form. And this integral over Z. Do you remember GZ was X? As a result, Z is G inverse X. So DZ is G inverse prime X dx. It has some proof, by the way. It has some proof. Okay. G, so this is, what is this? This is the derivative of G inverse X with respect to X. Okay. Now, as a result, let me replace Z here with here. G inverse X. These, so here, rather than, you tell me. So here, dz, rather than dz, I put this. Agree? Rather than gz, I put x. So d of gz becomes d of x. Agree? This is what we had. The relation of distributions of input and output is this. So pgx is pzz times g inverse x. I know I didn't give the proof for that, but there is a proof for that. Okay. Now replace z with g inverse x as before because of this. Okay. Also g inverse x, I'm repeating it here. Okay. You need to focus. There's a lot of calculations. G inverse x is the Jacobian of the distribution at point x. Anyways, it doesn't matter. This sentence doesn't matter. Don't confuse yourself with this. We have this. Now, let me do this. So this is what we have as V dgz. I'm repeating this from, give me a second. Oh, okay. Okay, just give me a second. Here, Do you remember this is what we had? Okay. Now, consider this term and this term. This times this, I just, according to equation 9, equals PGX. Do you agree? No? Where did you get lost? Did you understand up till here? Also, without proof, accept this equation 9 from me, okay? Okay. I mean, accept this part, and then I'm replacing z with g inverse x, okay? Now I'm telling you this times this is PGX. So here I have this times this. I replace it with PGX. Okay. And this part is here. DX is here. Agreed? Here also I have P data log DX, DX. Here there is a typo. Here this becomes X. Why? Because everything is now in this integral is with respect to X. Right. So I have two integrals with respect to X. I can combine them into one integral. With respect. Now, we want to do optimize equation 3. What was equation 3? I don't remember, but it was the loss function. The loss function. Okay. So what should we do for gradient descent and ascent in GAN? You should take derivative. Take derivative for the discriminator. I should take derivative with respect to D. For the generator, I need to take derivative with respect to G. So for the discriminator, I take this. And this was my loss. Right? So obviously, this is not dependent on D. Log of something, its derivative is the formula of derivative of logarithm. It becomes this. Agree? Also here, I have log of 1 minus D. Its derivative, because 1 becomes a 1 over 1 minus D. I have PG here also. So now I make the denominators the same. I combine the two fractions. And I set it to 0. Why? Because why?
Sorry, for optimization of the
Equation 3, I believe, is, let me go back. I don't remember.
second term has D is
This is the loss, right? So now I'm talking about this max D. Okay, with respect to D. Okay, is it clear?
what happens
To the G? No, in the theorem it says for a fixed G. For a fixed. Okay. For a fixed G, I'm assuming G is fixed now for now, and this. Okay. So now I should take derivative, set it to 0, right? To find the max. Set it to 0, then the numerator is equal to 0. So rearrange the terms, it gives you this QED. We just proved that. I know. I will also said that it makes sense, right? Now another theorem. The optimal solution of GAN is when the distribution of generated data becomes equal to the distribution of data. It's obvious, right? But it has a proof, right? Intuitively, it's obvious. When G is very good, PG star X is P data X, right? Well, let's see. Put the optimum D star X that we just found in the loss function. Okay, what do I mean? Do you remember? So this is VDG, but for D star. This is a loss, but for D star. So rather than D star X, I put what we had in the previous theorem. Okay. Now you tell me. So can I say this in the denominator? It's the denominator. I write it as times 2 divided by 2. Equivalent. Right? Times 2 divided by 2. Now I bring this log of 1 over 2 out. So I have this and this, because logarithm of AB equals logarithm of A plus logarithm of B. So I have summations. Then, so these two are simplified to minus log of 4, because log of 1 over A is minus log of A, and the rest as before. Okay. Then What is this? Integral of this is the definition of KL divergence between this and this. KL divergence is a measure of the difference of two distributions. It's not a distance because it's not symmetric. But when the two distributions are equivalent to each other completely, if and only if the KL divergence is 0. The larger the KL divergence, the more difference they have. Okay? There is no upper bound on KL divergence. So this KL divergence of this is this and this. This is a definition of KL divergence in continuous form. Agreed? Now let's continue. So this is what we found. Okay. KL divergence, I told you, has a flaw, and that is non-symmetric, being non-symmetric. So they have proposed something named Jensen-Shannon divergence, JSD, which becomes symmetric. So it makes KL divergence symmetric. Its definition is this. Now replace the P and Q, and you will see it will be the same as before. Okay. So this is JSD. I'm defining that. Okay. Again, if two distributions are equal to each other, JSD is 0. Otherwise, it's larger than 0. Now compare this with JSD. I can write these two terms as 2 JSD between them, between P data and PG, minus log of 4. Okay. So now you tell me what I want to minimize this with respect to G. Agreed? Agreed? This is my loss. What should I do? It should be minimized. Do you agree that JSD is a non-negative quantity? It's either 0 or greater than 0. So this is constant. I can't minimize it. Minimizing that, in the best case, it becomes 0. Agreed? So when this term is 0, the 2 behind that is just a scale, right? When this is 0, it means that these two are equivalent to each other, because two distributions are equivalent to each other if and only if their JSD is 0. So we just proved that. We just proved. Corollary. This is what we found in the previous theorem. Also equation 14. This is what we just derived, right? And we conclude that, so put VG star and P data into this becomes 0. As a result, V of D star and G star, both of them becomes minus log of 4. In other words, when you train your GAN, at the end, the loss becomes minus log of 4. If it converges, if. Okay, because it usually converges very hard, okay? Now, convergence and equilibrium analysis of GAN. It's a game in game theory, so it has an equilibrium. You can see equilibrium in game theory is similar to convergence, okay? If the discriminator and generator have enough capacity, okay, for example, they don't overfit, etc., and they have enough number of neurons and weights, and every iteration of the alternating optimization, at every iteration, the following occurs. What happens? The discriminator is allowed to reach its optimum, which was this. This was the optimum D. Agreed? Agreed? For a fixed G. PG is updated to minimize this. Agreed? The generator wants to minimize this, so PG is updated as stated in this loss that we found. As a result, and PG usually converges to P data because this wants to become 0, this term, right? Then D star X becomes half, which is completely confused. In other words, at the end, after convergence, the discriminator is completely confused, and the generator performs perfectly well. I also have proof here. So this is VD star G that we had. Do you remember? There are convex functions with respect to PGX. They are convex, okay? With sufficiently small updates of PGX, it converges to P data because this is convex with respect to PGX. So it has one global solution. Then the GAN loss, it can be restated as this. Do you agree that consider F to be a negative logistic function, which is this? I can replace it with this. Yes, you can replace it with anything which is increasing with respect to its input. Why? Because when I want to maximize this, I want to maximize f of d of x, it should be equivalent to maximizing d of x, right? So you can put any increased monotonic function. Anyways, I skipped this proof. I think this doesn't have much to say, but let me go in this slide. After satisfying several reasonable assumptions, which I skip, you can see this reference for details. Again, with loss function of equation 16 is locally exponentially stable. Okay, it's a stable. And now let's talk about Nash equilibrium in GAN. As I said, what was Nash equilibrium? The equilibrium in which the players don't want to deviate anymore. They don't wish profitable deviation. They're happy with what they have. Nash equilibrium is the state of the game where no player can improve its gain by choosing a different strategy, and they're all happy about it. So as a result, you tell me VD star G star, the best, okay, equilibrium, is greater than or equal to VDG star. Why? Can you tell me? So when G is optimum, but D is not yet optimum. Can you tell me why? Why do we have this inequality? Because D wants to maximize V. So D is not happy about it, maximizes that. Agreed? This is also less than or equal to V D star G, where G is not yet optimal. Why does this make sense? Because G wants to minimize V. Agreed? Okay. Empirical experiments have shown that GAN may not reach its Nash equilibrium in practice. So they use regularization techniques that we talked about. Many regularization techniques that we have, such as noise injection, such as weight decay, such as ReLU, dropout, etc. Batch normalization. Now conditional GAN. Okay, in GAN that we talked about, we said that we generate images or data. By the way, when I say GAN can be used for anything, not just for images, it can be used for speech, for anything. So we generate stuff, data. But what if I have classes? And I want to say, generate something from class 1, not anything random. Okay, then I should use conditional GAN. What does it do? It has changed its loss to equation 18. How is it different? It's conditioned on Y. Y is a label. Let it be one hot encoded class labels, where C is the number of classes. Okay? Did you understand? You know one hot encoding, right? So for implementing this, basically they say Do you remember we input X to the discriminator to say whether it's real or fake? Agreed? It says now concatenate the label at the end of the X and then feed the X and Y together to the discriminator. Okay, so we concatenate the one hot encoded label Y to the point X for the input to the discriminator. We also concatenate the one hot encoded label Y to the noise for the input of generator. So for both discriminator and generator, I concatenate the label to their input. In this case, the generator learns to generate data for that label, and this discriminator also considers a label for discrimination. Now in the test phase after training, what should I do? For whatever class I want to generate from, I make the one hot encode of that label. Then I also sample some noise. I concatenate them. I feed them to the trained generator. It gives me some data from that class. Okay. Idea is simple, but it works well. By the way, we have a lot of variants of GAN. I'm overviewing the most important ones. Deep convolutional GAN or DC GAN. Deep convolutional GAN or DC GAN, it was proposed in 2016. It made GAN deeper. They said, let's make it deeper and generate higher resolution images than GAN. Okay. It generated higher resolution because initial GAN was not very good in terms of resolution. It also showed that it is very hard to train GAN. They showed that it's very hard. Apparently, it doesn't converge very well. Okay. So they did a lot of trials and error to find out how to train a GAN. That's right. They used all convolutional network, so they didn't use any fully connected layer. Okay, they replace pooling functions with strided convolutions. Even the pooling was replaced by convolution. Okay. It has some justification. They say it learns its own spatial downsampling. Okay, it learns for this input, for this specific input, I need to downsample in this way. Okay. In DC GAN, we also have one convolution, only convolution layers, as I said. Okay. In the input layer of generator and output layer of discriminator, without any fully connected layer. And they have some inspiration for elimination of fully connected layers, reference 24. They also use batch normalization, except the last layer of generator and the first layer of discriminator. Can you tell me without looking at the slide? So we have batch normalization in the layers of generator and discriminator, but we shouldn't have batch normalization at the end of generator and at the start of discriminator. Why? What does batch normalization do? Do you remember?
Normalizes or unit like variance or
Yes.
mean zero.
So it standardizes the batch. So the mean becomes 0, the standard deviation becomes 1. The output of generator is like an image. If you standardize the image, it will ruin the image. The discriminator gets the image as input. The statistics of the image is important. You shouldn't ruin that. So the output of generator and the input of discriminator are important. They shouldn't. The statistics are important. And batch normalization reduces the problem of mode collapse. We'll talk about it. We'll talk about mode collapse. With the price of causing some fluctuations and instability. And they also have something named virtual batch normalization, which we skip. I think nowadays it's not that much important. Okay. In DC GAN, the last layer of generator has the hyperbolic tangent activation function. Why? They need to cap their output, right? As a generator. So assume that it's trained on images. It needs to give me grayscales between 0 and 1, right? Then you can consider it between the scale range 0 and 1 to be a range between -1 and 1. Doesn't matter. So they need to have some cap. So they use hyperbolic tangent because they wanted to also generate negative values as well. So they use hyperbolic tangent to be between -1 and 1. For the rest, they use ReLU activation function. Why? Because ReLU is a very good regularization technique. Do you remember? And also according to the Occam's razor and Bettina sparsity principle, this works well. As in GAN, one to last layer of discriminator is flattened and connected to one neuron with sigmoid activation function, as in original GAN. In contrast to GAN, which used max out activation function for discriminator, do you remember? They use leaky ReLU in the discriminator. They have tried different things and said that this works better. An interesting thing in DC GAN, I guess, was this. They showed that we can have vector arithmetic in latent space. What do I mean? By the way, they were inspired by word2vec. What did word2vec do? Word2vec was a technique in natural language processing. I already have explained this in this course a bit. That it says I embed every word as an embedding vector in some embedding space. Okay, they use, I think, a simple neural network, 1 or 2 layers of neural network, and it has the idea of logistic regression as well for training. But they have trained on huge data. So they have found some embedding per word without the context. So it's not a context-aware embedding. And then they said, for selling their idea, they said, consider the embedding of king minus the embedding of man plus the embedding of woman. It becomes almost the embedding of queen. Interesting. So we can have vector arithmetic on the words. Likewise, in this again, they said, why don't we have the same thing for images? Okay. They said, consider. So do you remember I told you that every latent noise corresponds to some image, real world image, right? Agree? So consider I get some latent noise which corresponds to man with glasses. I know this corresponds to man with glasses. Why? Because if I feed this latent noise to my generator, it gives me a face of man with glasses. Okay, so I know that. I also have noise for man without glasses. I search in the latent space to see where it is man without glasses. By the way, I have trained with GAN with all of the male and female facial images with and without glasses. Okay, so my latent space is kind of related to facial images of different genders and having and not having eyeglasses. Okay, so I search in the latent space. Somewhere it is man with glasses, somewhere is man without glasses. I take another noise, also find a noise with woman without glasses. Then what do I do? So I have 3 noises, 3 noise vectors. Can I have arithmetics between noise vectors? This minus this plus this, then it gives me a 4th noise vector, right? Then I feed the 4th noise vector to the generator. It gives me images of woman with glasses. Interesting. Man with glasses minus man without glasses kind of becomes glasses. Plus woman without glasses becomes woman with glasses. But as it was a bit unstable, rather than 1 noise per each of them, they use 3 noises. Average of 3 noises. Interesting, right? What is mode collapse? Again, we expect from a GAN to learn a meaningful latent space of Z, right? As I told you, what is meaningful latent or semantic latent space of Z? Every part of this latent space corresponds to something. And when I slightly move in the latent space, the output, generated output, is also slightly moved, which makes sense, right? Every specific value of Z maps to a specific generated data point X. Nearby Z values in the latent space should be mapped to similar but a little different generations. The mode collapse problem, also known as a Helvetica scenario, is a common problem in GAN models. It refers to when the generator cannot learn a perfectly meaningful latent space, as was explained. What do I mean? Rather, it learns to map several different Z values to the same generated data point. You get several different Z values and they are all mapped to the same thing, X. It's wrong, right? This is called mode collapse. It usually happens when in GAN, when the distribution of training data P data X has multiple modes. Its distribution has multiple modes. An example is this. They have trained GAN on mixture of Gaussians, a bunch of Gaussians, as you see here. It has a lot of modes, right? Each of these is a Gaussian distribution. Then, at different iterations of the GAN, different Z values, all are mapped to one of the modes. So, for example, step 1, all of them are generated, for example, this. A step 2, they all may generate this. They cannot generate the whole modes. This is called mode collapse. And another statement of the mode collapse is this. Assume P data X is multimodal, while the latent space PZ has one mode. Consider 2 points X1 and X2 from two modes of the data whose corresponding latent noises are Z1 and Z2. Okay. Then, according to the mean value theorem, there is a latent noise with the absolute gradient value is this. The L2 norm of X2 minus X1 over L2 norm of Z2 minus Z1. This is Lipschitz continuous, this gradient, by the way. I already have talked about Lipschitz continuity in this course, I believe. When the two modes are very far, resulting in a very large norm of X2 minus X1, we face a problem. In this case, the latent noises between Z1 and Z2 generate data points between X1 and X2, which are not in the modes of data and thus are not valid. So this is another representation of mode collapse. It says that by going from X1 and X2, there is nothing in between them in the real world images or distribution, but we generate them. This is wrong. So there are several ways to handle this problem. Some of them, what do you do? What if assume you face this problem? The simplest one is what? Do you remember? So P data X is multimodal. Let's make PZ data, PZZ, the noise, also multimodal. Make the latent space a mixture distribution, multimodal, right? These methods, there are some other methods too, such as mini batch GAN, unrolled GAN, Borgen GAN, mixture GAN, dual discriminator GAN, D2 GAN, Wasserstein GAN, W GAN. All of them I have explained in our tutorial paper. You can see the details in our tutorial paper. Now let's see some applications of GAN, some fun parts. Consider this. We can train GAN to do these things. For example, I have edges it colors it for me. The other way around is easy. You use edge detection. But getting edge and add color, adding painting it, in painting that is hard. GAN can do that. How do they train it? Of course, you need pairs of data where you have images and their edges. It's so easy to generate such data set. You have a bunch of images, colored images, and you apply edge detection on them. So you have these pairs ready to be trained. You have an image in daylight, you make it the same image in the nighttime, or vice versa. You have, I think this side is easy. You have an aerial image, you make it like a map. It's easy, you can do it by image processing maybe. The other way around is hard. You have a map, make it like real world data. It's also useful for Google Maps, right? They do it. They do it. Agree? What is this? Okay, this part is easy. You have a colored image, you make it grayscale. You know how to do it. It's an average between a weighted average between RGB. But the other way around is hard. You have a grayscale image, make it colored. RGB. They do it by GAN. How do you train it? Simply you get a lot of colored images and you make them grayscale by image processing, and you have pairs ready to be trained. You have zebras, you make them horse, or you have horse, you make them zebra. This is the coolest one. You make a sketch of face, you make it a real one face. Again, its data preparation is a bit tricky, but at least a portion of data can be prepared by having the facial images and applying some edge detection on them. These are generated by cycle GAN and deep face drawing. This is deep face drawing. Proposed in 2020. As you see, they are state of the art almost. This is a very cool thing. This paper and the next slide, I think, are proposed, as far as I remember, by a professor and his lab in, let me remember, in University of Southern California. Why do I remember that? Because when I was applying for my PhD, I emailed that professor. He answered me, but he never answered me back after a while, and he rejected me. Okay. I applied to his lab. So what did they do? You have text. This or the next slide, I don't remember which one. This bird, so you have text, you make an image for this text, or vice versa. So if you have image, you make text for it, it's called image captioning. You make captions for them. But the other way around is also cool. You have the caption, you make the image for it. Like the bird, this bird is red and brown in color with a stubby beak. It generates it for you. Of course, it needs to be related to the data set that you trained on. For example, they have trained on birds. So the text needs to be about birds. Or this small bird has a white breast, light gray head and black wings and tail. As you see, it has generated. You can see this reference. Proposed in 2017. Its method is called stack GAN. I have explained all of this in my tutorial paper. You can see that. This one is very cool. I think this was the paper that I was talking about. I applied to for my PhD. So you get background, you get shape, you get texture, it generates the result for you. So it takes background from some image, shape from another image, texture or color from another image, and it combines them. This is the result. So for example, this is an example. For background, get this, the background is water. For shape, get this shape. So that's why this shape is like this. For texture, get the color of this, which is black and red. It becomes this. Its background is water. Its shape is like, the color is like. Interesting, right? Here, this is another cool one. You can get appearance and shape. Appearance from a bird, shape from a car. The result will be a car with the appearance of a bird. Okay. Yeah, I think the professor was in this group. This is called mix and match. Okay. They are very new, 2020, 2021. Now let's see adversarial autoencoder. Previously, variational base was used in an autoencoder setting to have variational autoencoder. Unfortunately, there was no time in this course for me to cover variational autoencoder. In the previous semester, I covered in the statistical machine learning, I also covered variational inference. Okay, feel free to watch those if you would like. But likewise, we can implement adversarial learning in an autoencoder setting to have adversarial autoencoders. There are at least 3 adversarial autoencoders. One of them is adversarial autoencoder itself, AAE, proposed in 2015. Pixel GAN autoencoder proposed in 2017. Implicit autoencoder proposed in 2018. All of them proposed by Alireza Makhzani. He's now, he used to be a PhD student at the University of Toronto under Professor Brendan Frey, one of the biggest guys in AI. He was the supervisor of Ali Qudsi too, Brendan Frey. Previously, he was in the University of Waterloo. He moved to University of Toronto. So why do I remember Alireza Makhzani? Because I also, for my postdoc, I emailed him. He never answered me. Good times. Okay, so adversarial autoencoder was proposed in 2015. This is the structure. So what do we have? Let's see. We have, do you remember for autoencoder, we have encoder and decoder, agree? So we have encoder and decoder. And usually we have X, we reconstruct X by X hat in the decoder. And in the middle, we have some latent space, agreed? Now, let's combine it with adversarial learning. In adversarial learning, we have a generator and discriminator. Let the encoder of autoencoder be also the generator. Do you remember the generator? We have generator and discriminator. So for discriminator, I have another network. I have another. Okay. So 3 parts I have: encoder, decoder, generator, discriminator. Encoder and generator are the same thing. Okay. Now what do we do? You tell me. Right. You tell me. So my encoder gets X, outputs Z, right? Interestingly, in adversarial autoencoder, I want to generate realistic noise rather than realistic data. Do you see that? So I generate Z. I also have some prior Z. My discriminator needs to find out whether it's a fake Z or real Z. What do I mean by realistic noise? It doesn't make sense. Let me tell you what I mean. By realistic noise, I mean I want the distribution of this noise to be similar to this noise. Okay. So assume my prior noise is Gaussian. So I want in the middle to have a Gaussian noise distribution. Okay. And if this works well, it will fool the discriminator. So I can use the loss function of GAN. So it has 2 loss functions. As I said, it wants to fool the discriminator. If Z, this is what D of Z is supposed to say with the eyes of discriminator. If Z is real, which is here, it outputs 1. If Z is generated by the encoder, it should output 0. Agree? So What loss functions do we have? Of course, we have two loss functions, one for reconstruction and one for adversarial learning. Agree? So it's an alternating optimization. So basically, this loss function is for mean squared error for reconstruction. These two are the gradient distance for generator and adversarial and discriminator of adversarial learning, right? Agree? Note that for the reconstruction, only B1 and B2 are important. So I have these two. For the discriminator, B3 is important. For the generator, B1 is important. And it is alternating. So B2K plus 1 here. No. B1 prime is used here too. But at the end, I will have this. So B1 is updated twice. These are called reconstruction phase and regularization phase. We can also have supervised adversarial autoencoder and semi-supervised adversarial autoencoder. For that, see our tutorial paper. Okay. Acknowledgement. Just give me a sec. Some slides are based on our tutorial paper, Generative Adversarial Auto Networks and Adversarial Autoencoders Tutorial and Survey. For more information on GAN and its variants, see our tutorial. It covers various variants of GAN. So it covers all of these. See, vanilla GAN, conditional GAN, DC GAN. We saw these in this course, right? Mode collapse, we saw that. Mini batch GAN, unrolled GAN, Bohr GAN, mixture GAN, D2 GAN, Wasserton GAN, F GAN, adversarial variational Bayesian GAN, feature matching in GAN, info GAN. Info GAN uses information theory too. G-GAN, LS GAN, energy-based GAN, CAT GAN, MMD GAN. What is MMD? Maximum mean discrepancy. For one of the methods for finding out the difference of two distributions is maximum mean discrepancy, proposed by Sholkov et al. In Max Planck Institute, the god of kernels. What is LAP GAN? LAP is short for Laplacian pyramid. Have you seen Laplacian pyramid in computer vision and image processing? So you have an image, you can make it smaller and smaller and smaller. So LAPGAN says, let's generate it in higher resolution, then a bit smaller, then a smaller, generate images in different levels of the pyramid, Laplacian pyramid GAN format. Progressive GAN, triple GAN, lag, G-man, ADA GAN, co-GAN, inverse GAN, bi-GAN. Bi-GAN is bidirectional GAN. Ali, Sagan, few shot GAN. Few shot means you can train it with few samples for training. Scene GAN, interpolation and evaluation of GAN, image to image translation. I showed you some examples of applications such as patch GAN, cycle GAN, deep face drawing, simulated GAN, interactive GAN, text to image translations, including stack GAN, mixing image characteristics, fine GAN, and mix and match, adversarial autoencoder, pixel GAN, and implicit autoencoder. And some slides are also inspired by teachings of Professor Ali Qudsi at the University of Waterloo. And these are all of the references that we have. Feel free to see our tutorial paper. We have 5 more minutes. I can cover one tiny thing. Do you want me? Do you like to know about knowledge distillation? No. Knowledge distillation, do you want?
Sure.
Are you tired? I want to teach you as much as I can. Although I'm tired, I'm really tired.
Oh, it's fine.
I'm dying of tiredness, but I want you to learn as much as possible. So let me tell you the idea. I don't go into the details, okay? Assume, so I want to compress a network. I have a big network. such as BERT. BERT is big, right? I want to compress it. Why is network compression important? Smartphones, exactly. So for embedded systems, we have limited memory. You can't have huge amount of weights, right? So you need to compress it. Then the idea is this. It says, I have a big network, very big network. Also have a smaller version. So I have the big network already. I have the big network, okay? But so let me say big and small. I have the big network already, but I want to make a small network out of it. How do I do that? You tell me. I have some data set as well. Data. So the idea is this. Assume you want to train a small network with whatever you have, such as assume it is classification, so you can use cross entropy, for example. So you use that. But you add this, you regularize it with some other loss function. And what is that? You want the output of this to be similar to the output of this for the same input. You want the small network to imitate or mimic the big network. Agreed? So you have two parts in the loss function. Your own loss function, cross entropy, for example, and then the KL divergence between the outputs of big network and small network. In this way, you are distilling knowledge from the big network to the small network. Now you tell me. So we have this thing. Now you tell me. We have different ways to do that, by the way. Another way, for example, is that we first do some. We say initially, try to imitate the big network. And after a while, forget the big network and only do cross entropy. Okay, rather than regularization, you can do this. There are several ways to do it. Ali Qudsi has proposed a lot of algorithms on that. We have other variants of boundary distillation too. But let me tell you one important thing. There is some problem for knowledge distillation, and that is gap problem. What does it mean? Assume I have a very big network. You're working in a smartphone company. Your manager says we have too limited memory. So you have to make your network very small. But that is very big. Can you distill from that big network to the small network? It doesn't work well. It won't work well. It's hard. So what do? Assume your big network is called teacher. Your very small network is called a student. What do you need here? A teacher assistant. Teacher assistant, right? This is exactly what they called it. So we have teacher network. We have a student network. By the way, those networks are actually named teacher network and student networks. In the middle, I can have a middle-sized network. This is teaching assistant or teacher assistant network. I distill knowledge from the teacher to the teacher assistant, and then I distill knowledge from teacher assistant to the student. Now, assume the gap is too large. I can have a hierarchy of teacher assistants. Teacher assistant 1, then teacher assistant 2 becomes a smaller. Teacher assistant 3 becomes a smaller. Okay. So teacher assistant. It was proposed in 2020. You can see it's very state of the art. Also, another problem is checkpoint search problem. So it has been empirically found out that not necessarily the last iteration of teacher network is best for training the student network. Who says that? Some intermediate epoch checkpoint of teacher may be better to use. So what should we do? This needs a checkpoint search in the teacher net, right? Agreed? But this is a problem. How many checkpoints should we check? This is a checkpoint search problem. Alternatively, we can have 2 stages where we train the teacher and a student together simultaneously. Let's teach them simultaneously, right? By the way, we can have attention between the student and teacher. Why do we need attention? Do you remember? What was attention? Do you remember? Transformers and attention that we talked about, right? Now you tell me, assume I want to, rather than loss between the outputs of the teacher and student, I want to have loss between all layers of the student and all layers of teacher. But this doesn't make sense because the number of layers in the student is much less than the number of layers in the teacher. So what should I do? I can calculate the attentional, the weighted difference or weighted similarity of every layer of this student with the other layer or with all layers of the teacher. So I can use attention, which was weighted linear combination. It's very interesting. We have survey on KV knowledge distillation. And these are the reference. Okay, the course finished. I hope you enjoyed it. How did you find the course? Honestly. Really?
Yeah.
Did you enjoy it?
Very interesting.
Thank you. And please feel free to advertise the course and feel free to take statistical machine learning if you haven't. And please feel free to give me feedback if you haven't. Thank you. See you on Friday, yes? On Friday for presentation.